to the organizers of this long-standing meetings. It happens in the spring usually, right? But I appreciate Wojtek the invitation to be here. We're going to talk about something that may seem a little strange. I think it's a new idea, that is to use the mathematics of transport and optimal transport represent data. And we're talking about sensor data like image pixels, in signal intensities directly, just in the same way that you think of the Fourier transform as a representation tool in a certain set of bases. We're going to use that mathematics to represent this data, and then we're going to ask questions: what good does it do? Before I begin, like to thank many people that have helped us with this project. It's a project I'm presenting several ideas from the past few years. Some of these people may be known to some of you, at least 2 or 3 particular advisors from past advisors, including Professor Aldruby, Professor Healy, Professor Bernstein, were patient enough to try to teach me things. Whether I actually learned them or not, it's up to debate. This is a picture of our lab in the past 2 or 3 years, and I'm very thankful to all these people, too many to mention one at a time. So, what are the big questions? There are many. One of the big questions that people are attempting to do in science and technology these days is to build what's called smart systems, right? We'd like the sensor to make the best use of this sensors and sensor data that are available to us to do interesting things: detect pedestrians, maybe help cars drive themselves, help doctors find cancers more accurately, more timely, more cheaply, right? Future applications may be, video-based things to detect if you've had a stroke or you're showing signs of stroke. Many interesting things to do. People are pursuing pretty hard. And the temptation nowadays is to try to do this. Try to do this on the cheap, for lack of a better word. The temptation is to try to use machine learning and bypass, to a large extent, any kind of bottom-up, grounds-up approach, and instead use the data together with some mathematical modeling to see if we can speed up the processes and arrive at these systems in some fashion. But there are a lot of problems, right? And I believe we've just begun looking at this more seriously. There are many examples that show that a lot of the so-called artificial intelligence that gets applied to this problem, these types of applications, have a lot of problems. You can classify an image pretty well, but you add some very tiny, minor noise perturbations, imperceptible to the human eye, and you get these technologies to make very confident but very wrong predictions. Right here is a famous study where they took one of the earlier on face recognition methods from Amazon, and took the top 10 most wanted people in the country and run it through the Congress and make a lot of matches. Whether those are sensible matches or not, we can discuss them. But same things get repeated with COVID detection. Here's an interesting video showing actually a little bit the problems, right? So you can see that this person detections works pretty well, but it doesn't work for this guy because he's wearing a funny shirt or a picture in the shirt. Why did that happen, right? These are called so-called adversarial attacks, and when the person takes this off, you can see it starts working for some reason, right? So now a big effort to explain why this is happening, when it happens, when it doesn't happen, and so on, right? But the problem is that when this gets actually applied to certain things, right, out there, you will see that this can be a kind of a mismatch. This kind of idea for critical systems in medicine, biology, navigation, and so on, right? So I think we'd like to build technology that we have some kind of better answers, right? You want to know when they work, you want to know when they fail, you want to know why they work, you want to know why they fail, so that, if you have some underperformance, you have a path, you have ideas about what to do to improve, ideas that go beyond just get more data and more layers, right? We need to do better. So this project, as I said, we're going to try to play some ideas in this realm to utilize this tricks for representation where, we have data in signal space where a problem may be hard to solve, this detection of persons, cancers, and so on. How do you actually solve it? And under some assumptions, we're going to transform them to a new space, solve it there, and hopefully we have properties, mathematical ones that can be shown that where these things can work better. And if we would like to see what the answers are back in signal space, we apply the same trick of free analysis and invert it back. Right? This is not a new pipeline, not a new idea. And in fact, we've been working little by little for almost 10 years, but especially intensified in the past few years. So here's the basic idea, right? Let's say we have a signal. This is a one-dimensional signal here, say a probability density function. And this is a signal we would like to analyze or represent in this case as the first instance. And let's say we have a reference signal. Let's say, for analysis, your reference signal is your sinusoidal basis function, right? So let's say we have a reference signal here too, and this could be the uniform distribution. We can apply a very simple basic change of variables in probability distributions to find what is the map that I need to push forward this density onto that one. And if I know the reference and the match push forward, the push forward map, I can also, yeah. How do you turn it on?
There's a switch on the top.
Oh, yeah, there you go. Is that better? Sorry about that. So if you know the push forward of this measure onto this measure, right, then you can take the reference measure and invert this map and get the map back. So in that way, you can think about an assignment, a one-to-one correspondence between probability density functions and diffeomorphisms, right, with certain assumptions on the smoothness of the input probability space. This can be done in one dimension, and in two dimensions with uniqueness theorems from optimal transport, these push forwards can also be defined, right? So just like you think of a Fourier transform, for example, as a map from one L2 space to L2 space with one-to-one correspondence, inversion formulas, etc., this framework also allows you to do that. This is a mixture of engineering and applied math talk. So let's do a very, very basic calculation here. Let's say we have two signals. These are 1D functions, and for now we're going to assume they're smooth and they're probability density functions, right? Your standard probability functions. To make things easier, I'm also going to specify that they must be greater than 0. Now let's define this map that matches their cumulative integral, right? So let's on the reference signal, which I call S naught, I go up a value of x and I compute the area, and I've asked the question, what is the f of x on this axis where the integrals match, right? So this is a simple integral matching equation. Look at this, consider the integral, the antiderivative of this PDFs, your cumulative functions, right? And if they're positive, these cumulative functions are one-to-one. You can talk about an inverse existing. And so you can define this map, this push forward map that I just talked about, as simply the inverse of the accumulation of your signal applied to the accumulation of your reference, right? And this map is, in this case, what we're talking about as a transform, or your way to represent your original signal, knowing what reference you started with. Simple example, if you say your reference is just a uniform probability function, let's say your chi function between 0 and 1, your integral in that domain is simply x, right? And your map is simply the inverse of the cumulative function of your signal, right? Very, very basic things. So now you have forward equations and inverse equations, just like you would have in a wavelet transform and the Fourier transform, and so on, right? So summary of the story for us engineers, we're like pictures. Here's your signal. Here's the accumulation. Flip the axis, right? That's basically what we're talking about here. There are numerous extensions of this basic idea to 2 dimensions and 3 dimensions and so on that we have worked on. I'm showing you some of the simpler ones here, where, for a 2D image, we can combine this technique with a Radon transform, right? Another type of transform here where you take a 2D function in Cartesian coordinates, you write it in terms of integral projections, right? That's the forward Radon transform. This forward also has an inverse, right? Which is known as the filter back projection. You take each of these projections, filter it with ramp filter, and then back project, integrate. There's a forward and inverse map of these things. So we can take an image, take the forward on transform, and apply this cumulative distribution transform I just talked about line by line along the theta axis. And since each of these is a one-to-one mapping, I can go from the transform domain back to the image domain, just as I would with a wavelet transform or Fourier transform. This is one of the extensions. There's several that we have worked on. Why are we doing this? Like, just as you think of Fourier transform having some properties, like you have a shift property of Fourier transform, you have your derivative property, you have your scaling property, and so on, right? You have some of these properties of these maps as well. Here's a translation map, right? So if you have a density here and you have a translated version of this density here, slide it to the right, here are the accumulations, and you flip the axis, right? So translation in this domain in the independent variable now becomes translation in the dependent variable. Scaling, similar stuff, right? You have the scaling functions here. So, and whatever the transformation is that you apply, as long as you apply this composition here or this push forward for densities that you have here, right? Whatever Lagrangian displacements you do in your signal domain, according to this push forward formula, will become Eulerian displacements in your transform domain. And this is the basis of some properties that we have investigated to help you analyze the geometry of these data sets so that you can do your so-called machine learning in an easier fashion, right? So let's look at the set of the family of functions that are composed of this simple Gaussian, this dotted one, and all possible translates of this Gaussian, right? What does this set look like? First of all, it's a non-convex set, right? In the sense that I cannot take a convex combination of two elements of the set and end up with an element on the set. Another way to see this is that if you take all these functions as training data and do a linear projection down to some lower dimensional space, take your PCA or other technique, you're going to see that this data comprises a nonlinear structure. It's not a convex structure. It's not a linear submanifold, right? If you take the transform of this data, the way that we just talked about, you can justify from the properties that we just talked about that you'll see now this has become a convex space that can be modeled more easily by linear vector spaces. We can use this as building blocks to arrive at certain theorems that may be useful to do machine learning. So let's talk about a typical machine learning problem, which is the problem of separating sets, right? I would like to find a function. The easiest one would be a linear functional. But either way, I would like to find a function that separates two classes or two sets, right? Let's say you have class P or set P and class Q. And let me propose a model that from what the data that populates the sets was generated. And here's the model. We have a template function. Here we have a function of one bump called P naught. And we're going to say that all elements of class P are observations of this template under some unknown push forward transformation, right? And in this case, we're using translations, right? Class Q is another template called Q naught, but the elements of this class are unknown functions. The elements of this class are unknown deformations applied to this other template. If we do a projection, a linear projection of this, you can see that to separate these sets, I'm going to have some kind of nonlinear function here. I'm going to have to fit something very complicated nonlinear, right? Even though it's a very simple, pedestrian, mundane kind of problem, right? It's just translation. Can we solve it? Yes, we can solve it, but I'm just providing a simple example, right? But if you look at the same stats in transform space, you have these lines. Almost any linear function, you can choose one at random and it will work, right? So you can facilitate dramatically the solution to several of these machine learning problems. This doesn't only work in 1D, we can expand this to 2D, 3D data as well with these other projections. And here it's the same kind of problem. We have images of one dot randomly placed in the domain, images of two dots randomly placed in the domain, images of three dots randomly placed in the domain. And then if you try to apply your linear classifier here, it's going to be a mess. You can actually show mathematically this is not linearly classifiable. And if you apply this Radon CDT transformed, you can see that it's in theory, you should have that it's possible to do linear classification, right? We haven't said how, but it's possible to find a linear function. And in fact, if you try many of them, almost any of them will work. So, there are separation theorems that one can build like this, and we have several flavors of them. There are several publications where we investigated different options, but here's the gist, right? If you have the signal classes that are generated under this generative mechanism here, and you say you have C, your group from which your push forwards are being functions is a group, convex group, and so on, then this type of transform that I just described will generate convex sets. Right? So those are nice things to have. And so now if you're looking at a machine learning problem, you ask yourself a question: was data generated from this kind of model? That you can borrow a little bit of physics, right? You can look at the problem, how is this data generated? If it's generated according to that, this is a good idea to do, because then you can even apply a linear classifier in transform domain. It should work. You don't need to worry about fancier stuff. All of the stuff that I'm talking about, half an hour is not enough to do virtually anything, but it has clear, deep connections to the theory of optimal transport, right? So there's another language that we can use to describe all these concepts that I'm talking about, which is related to some kind of linearization of these Wasserstein spaces. If the square Wasserstein distance can be seen as an infinite dimensional Riemann manifold, right? And this reference business, if you take a reference, it's like you're finding a tangent plane identification of your data onto the tangent plane. It's like this cartography projections, right? You have your globe and open up the map, right? You can go back, but there are distortions. So this is essentially what's happening here, and it's connected to the theory of optimal transport. And this was actually our first paper in this area that motivated all these ideas about transforms and so on. So long story short, you have data, can be tough to classify. If it comes from a transport related process, some kind of push forward of some template or templates, you're in good shape now, because now you have a transformation that will linearize this problem for you, right? And essentially what it does with signals and images, it gives you a new geometry, right? And it allows you the ability to have pixels look around, right? So for example, if you try to do a Euclidean geodesic between this function and that function, or this image and that image, what you get is a ghosting, right? You have this transition between these two endpoints will be the linear combination of them, right? That if you do the geodesic in this Wasserstein space, you will be moving these points, right? And the transformation that we're proposing here, the kinds of transformations, take you from this weird manifold space into a Euclidean space where you can do this convex projection there. But if you want to visualize, just apply the inverse transformation formula and everything becomes doable. Applications, there are tons, but the type of problems that we're looking at are these type of data sets of faces, cells, brains, organs, digits, EKG signals, all these objects where this idea of having a template and observing that template under some push forward, some deformations, where those apply, right? We have a common anatomy for the face that works for 99% of the people. Same thing for the brain, same thing for the EKG signal. Now there are variations, there are pathologies and so on that have to be modeled. But the starting point of view of a template observed under some different deformations, I argue that is a good starting point, and perhaps better than assuming that brains are made up of sum of wavelet functions, right? So what are the problems? So the question is to ask, what is a good mathematical model to represent all of this data so that you can solve the problems that you want to solve? So, how, and furthermore, given this representation, how do you partition these classes, right? That's, if you can do these problems correctly, then you provide a lot of help, and maybe your cars won't be driving over children anymore, right? So the point of view of having this generative process is exactly this, right? If you have a template here, phi here, and you apply this generative, this deformation, you will end up with a different template, right? And you have the same thing here. You have a cell, you apply some kind of deformation, you have a different cell. This is the type of thing, right? That, data set. If you're looking at this data set, you should have an intuition, does this idea apply or not? In this case, these ideas apply. So how does a classification problem look in a little bit more detail? Let's say take your famous MNIST classification data set, right, from the late 90s and so on. They put all these handwritten digits up online. There's 70,000 of them. People can have a lot of fun trying to create these maps to separate these classes, right? Here we're imparting a generative model on them that any object belonging to a class can be modeled as a template. Observe that there's some unknown variation. And now you can look at this data, look at the model, and ask yourself, is this a good starting point or not? Right? I argue that it is. We learn that way, right? We go to school and we learn what the digit 1 is. Now there are different ways. There are different calligraphy, different methods. Some people can put the little line at the bottom. Some people forget. Some people put the line on top. So perhaps the same class can have 2 templates, right? But everything else, a rotation, some bigger, some smaller, some squiggle in the middle, can be modeled as a deformation, a push forward of that initial distribution of ink on the paper. Doesn't apply only to this kind of imaging. We're looking at cells, brains, tissues, discover differences in cancers, but the same observation holds here, in part because these are physical processes where the continuity equation applies, right? And the continuity equation is essentially a push forward on a distribution that is initially, right, and things go forward in time. Now there are sources and sinks, there's chemistry involved, that part of the model is being left out, but nonetheless, this is a good initial starting point. We're also using this in general as a general transform, right? So we can do signals, images, any data set that has an independent variable that is in continuous form, right? Time is continuous, space is continuous. So the solution that we propose for this machine learning as outlined here, you have your signal space, it's hard to solve, right? Maybe you try to solve convolutions. Convolutions are hard to solve in time domain. Maybe I take the Fourier transform, they become multiplications, you know, the operator has been diagonalized and I can invert it very easily, right? Machine learning problem, hard to come up with these decision surfaces in signal domain. For some of them, if the data is generated according to this continuity equation-based physical process, you have this transformation now where the problem becomes easier to solve. In some conditions, you can guarantee that this becomes linearly separable. If you want to visualize your classifier, just invert it. So here's a problem statement, right? You have classes. You don't know anything. You're given data, right? You're given MNIST digits, digit 1, digit 2, etc. That's what you're given. That's your starting point. You don't have a physicist on call to say, hey, how was this generated, right? But that's your starting point, and you apply this technique. The gist of the solution is you perform this transformation. Now you have subspaces, and you can take a linear classifier, near subspace algorithm. Everything should work much better. Training and so very simple thing. Transform. You can even enrich your classes if you know translation should be classifier should be invariant translation. Add a vector that encodes translation in there. You have flexibility. You know what to do because you know the math. And it tends to work really well, right? If you compare this against the latest and greatest neural networks, look at the classification accuracy as a function of training data that you need to get to a certain classification accuracy and so on. Most of the time, these methods are doing significantly better than most of this deep learning. So a lot of improved properties in respect to auto distribution, right? That kind of stuff, like if the children was wearing a funny shirt or a funny pants and walks inside of the car, that's the data is out of the distribution. Right? That's why it doesn't work. We do a lot of these tests, and you can see this red curve, which is our curve, tends to outperform quite a bit. Computationally, right? Also, you want to do this on mobile devices. You can't have a fancy GPU all the time with you. So also you can show 3, 4, 5 orders of magnitude improvement in the computational solution that you have. There are limitations that the data must follow the generative model, right? That for this transformation. Otherwise, it doesn't work. And if you just take a CIFAR10 or some ImageNet data set, you can show that this approach is not optimal. It doesn't match what you can do with other techniques like deep learning. Long story short, for this kind of problems where you can see that your data is being observations of single template under some deformations, you have a map that can help facilitate these things. There's software. If you go to Google, type PyTranskit, the software is available for you to perform these transformations, for some of these classifications. And I'll just end with some invitation or clarification of some ideas of where we're going, right? So far, we've looked at this template and the deformation. That doesn't apply to a lot of problems, right? If I take a picture of all of you guys, what's the template for this room? How many fit? doesn't match, right? So can we push this math forward toward that domain? And start by this is a harmonic analysis crowd, right? So in the past, we've done this thing quite a bit of times, right? So we have this temptation to look at data and model data as linear combination of basis elements, frame elements, etc. Right? You can plug in your favorite wavelet, and the hope was that by thresholding some coefficients there, that might be enough linearity to solve some of these complex problems. We know that's not the case right now. Now we can do some compression work, you can do some other things, but if you're talking about building classifier, these detectors for complex situations, I think most people have wavelets is not the first thing they think of doing here, right? But we can merge two worlds in the sense that now we have the signals that don't have templates. We can propose these localized versions of these CDT transformations, these optimal transport representations, just in the same way as you think of the short time Fourier transform, right? To have a little window, you apply your CDT there, maybe locally it applies. Locally, your template model might apply, right? Same thing with images, you can do a local ridgelet or local curvelet. Same thing may apply there, right? So that's one of the ideas we're trying to go towards futures. There's plenty to do here. We're always very excited to work with mathematicians that really know stuff. We're very slow, so we need a lot of help to do these things. There are a lot of open problems. I just try to introduce the project here, maybe try to get some interest. Hopefully, if you would like to collaborate, we're here. And I'll just end with one simple warning, right? That opportunity is missed because it's always dressed in overalls and looks like work, right? So this is a completely different field, different idea. You step in there, you're going to be alone for a little while, right? So there's a lot to do, though. It's very fun. It's a completely new direction, and I'll end there, and I'll thank you for your attention.
Thank you, Gustavo. Any questions or suggestions or comments?